Hello everyone. In this video we'll go over the first part of Unit 4-5 where we'll talk about using the Laplace transform to solve some initial value problems. And then in another video we'll go over some unique properties of the Laplace transform in which you'll see later in the section. Okay, so to begin, here we're just recapping some identities of the Laplace transform. We're now going to apply all this, and if you've been working on the 4-4 homework, you might have already done problems like this, but here we'll do a couple and just to show you how it all ties back together. So the first thing we're going to do is suppose that we have, let's say, a saloon door, like old-timey saloon. Its motion is going to be given by this differential equation. Notice it's essentially a spring mass system. And we have this forcing function, so this driving force here, given by the function 60 cos t plus 40 sine t. And we'll see how that affects the behavior of the saloon door for large time values. Okay, and then the initial conditions are the initial position of the door is at 4, and its initial velocity is -1, which means, like, if we take this from the perspective of, let's say, someone outside the saloon looking at the door, position 4 probably means like away, but it's moving back towards the person at 1 unit per whatever time unit we're using here, probably second. Okay. So here's how we start off by solving the problem. We're going to apply the Laplace transform to both sides. We've done this many times now. So let's see what we get. Well, the left-hand side, that's going to be the Laplace transform of y double prime. So look on your chart. That's s squared capital Y of s minus s times little y of 0 minus little y prime of 0, right? And then we get plus 7 times parentheses the Laplace transform of y prime is s capital Y of s minus little y of 0, and then plus 10 times capital Y of s. That's what the Laplace transform of 10y is. And now this equals, well, look on the chart for the cosine and sine identities. The Laplace transform of cosine, that'll be 60s over s squared plus 1, and then plus 40 technically times 1 over s squared plus 1, right? Okay, and now we plug in the known quantities. We know that y of 0 is 4, y prime of 0 is -1. So here's what I get when I work all that out. So on the right-hand side, note the common denominator s squared plus 1, so I just throw both of those onto the same fraction. Here I get s squared times y of s, so there's that part right there. 7s times y of s, that's that part there. And 10 times y of s, that's that part there. Y of 0 is 4, so I get minus 4s. Minus -1 becomes plus 1. And then you'll notice I also have minus 7 times y of 0, so minus 7 times 4 is minus 28. Okay, and so if I simplify this just a little bit farther, you'll notice I get minus 27 here, and so that tells me that y of s times s squared plus 7s plus 10 equals, now if I add 27 to both sides, and add 4s to both sides, I get the following. And now to solve for y of s, capital Y of s that is, just divide both sides by this expression here, s squared plus 7s plus 10. All right. Now what we're going to need to do is we're going to need to find a common denominator. You'll notice that both of these fractions have s squared plus 7s plus 10. But this fraction would need a factor of s squared plus 1. And so what we're going to get is something like the following. And if you'll allow, I'm also going to factor s squared plus 7s plus 10 is s plus 2, s plus 5. And you'll notice that the 4s plus 27 will need the s squared plus 1, but the 6s plus 40, its denominator hasn't changed one bit, right? Okay, now we need to decompose this using partial fractions. So I'm going to actually do the linear factors first and then save the irreducible quadratic to the end. So it's going to be a over s plus 2 plus b over s plus 5 plus cs plus d over s squared plus 1. And you might be wondering, like, do we need to do any of that business from the previous videos where we had like c times s minus alpha plus, b times beta or something? And the answer is no, because if you look at this, your beta value is 1, right? What number squared gives you 1? Well, that's 1. And your alpha value is 0. So this is, in the proper form, c times quantity s minus 0 plus a constant times the 1, right? Which is beta. Okay, so recombining into a single fraction, let's just compare the numerators, right? So I'm going to get 60s plus 40 plus 4s plus 27 times s squared plus 1 equals, and now let's see what needs what here. Well, the a is going to need both the s plus 5 and the s squared plus 1. The b will need the s plus 2 and the s squared plus 1. And the cs plus d will need both the s plus 2 and the s plus 5. And so I'm going to plug in some numbers here. You'll notice if I plug in -2, that will knock out these two last terms here, and so I'll be able to solve for a. So if s equals -2, on the left-hand side, I'll leave you to verify this, I get 15. And on the right-hand side, I get a times -2 plus 5 is 3, and then -2 squared is 4 plus 1 is 5. So I get 15 equals 15a, so a is equal to 1, right? That's a 5 there. Okay, now let's try s equals -5, because that will knock out this term and this last one as well, so I'll be able to solve for b. So plugging in -5, I get -78 equals b. Now plug in -5. -5 plus 2 is -3. And then I get -5 squared is 25 plus 1 is 26. And you'll notice that this is b times -78 has to equal -78, so b is also 1. That's nice. So plugging in s equals 0 now, on the left-hand side, you'll notice I'll get 67. And on the right-hand side, I'll get a, which is 1 times 5 times 1, plus b, which is 1 times 2 times 1, plus, now you'll notice I just get d here. Notice c times 0 is 0. So I just get d times 2 times 5. And all of this is to say that 10 times d equals, and now I subtract 7 from both sides, equals 60. And so d equals 6, right? Okay, and you'll notice that I could plug in any other number that I want. So I'll choose s equals 1. On the left-hand side, I get 162. And on the right-hand side, I get a, which is 1 times 6 times 2, plus now b is 1 times 3 times 2, plus, and now c times 1 plus 6 times 3 times 6. And all of this implies that c is equal to 2. I'll leave you to verify that. Okay, so I left the next page blank so that we can have more room to work on this. So now let's write y of s in terms of our decomposition. So capital Y of s, well, remember it was a over s plus 2, so 1 over s plus 2, plus b over s plus 5, remember b was 1, plus, and then c, which was 2, s plus d, which was 6, all over s squared plus 1. And it may be helpful to split this up, right? This is 1 over s plus 2, plus 1 over s plus 5, plus 2s over s squared plus 1, plus 6 over s squared plus 1. And the reason is this is a cosine. This first half of the final fraction is a cosine inverse Laplace, and this one here is a sine identity. So that means that little y of t is the Laplace inverse of 1 over s plus 2 plus the Laplace inverse 1 over s plus 5 plus the Laplace inverse 2s over s squared plus 1 plus the Laplace inverse of 6 over s squared plus 1. And so solving all of that, this here is e to the minus 2t. This one here is e to the minus 5t. This one here, I can factor out the 2, and then I just have a cosine identity, so this is 2 cos t. And then this one here, I need this to look like I need a factor of whatever this b value is here. Well, that's 1, right? So 6 is already 6 times 1. So this is really just 6 sine of t. And there you go. So now if we go to the next page, notice I give a lot of room, it says in Desmos plot y and y prime versus t. I actually have that, so let me bring that up. So here is the graph of y, and so starting at time 0, you notice here we're starting at distance 4. Okay, so we see the door oscillating back and forth, and you'll notice that even though there are exponential terms here, as t gets larger and positive, these terms go to 0 very, very quickly. And so really all we're seeing is the oscillatory part, right? The sine and the cosine part. And that's indicative of the fact that we have this forcing function essentially pushing the door continually, right? And so here we go. And now if we look at the velocity, which I had to call g of t for reasons, I guess, we see that it has an initial velocity of -1. But something interesting that we're seeing here, and this will feed into the next part of the exercise, you'll notice that velocity is at a maximum, either negative or positive. Pretty much it lines up almost perfectly, and this lines up better and better as time gets larger, with when the door is passing through its sort of neutral state, right? Or sort of its natural state, I guess you would say. And so that should make sense that the door is swinging fastest when it's essentially passing through its middle there as it swings back and forth. And so the final exercise here is to just describe the behavior of the door, and I say as time goes on, only the trig portion of the solution matters, since the exponential portion becomes negligible. The doors driven by the forcing function oscillate regularly, and by looking at the graphs, we see that maximum velocity occurs as the door passes through its neutral position. Okay. So that's it for this video. In the next video, we'll do the next example, and then in the video after that, we'll learn some neat properties of the Laplace transform.